Hello friends, so today we are going to continue solving say 2 questions for rotational motion, and the first question we are given that a uniform stick of mass m, length L, rotates freely on a smooth frictionless table with center of mass stationary but not fixed to any pivot. The stick collides elastically with a stationary ball of mass m. At what point along the stick, measured from the center, should the collision occur so that the stick has no rotational after the collision? So it means after the collision, the stick should not be having rotational motion associated with it. Okay, so that's the basic question. And we can just draw the basic figure for that. So this is the stick and it is having a length of L and its mass is m, and it collides elastically with the ball, and ball is also having a mass m. Okay. And we have to find out the distance with respect to the center of mass. So let us suppose this is the center of mass of the stick, and so in this case we assume that if omega is the angular velocity of the stick, so we can say that our stick is spinning about the center of mass with, and minded the center of mass is ever stationary, okay, about center of mass with angular velocity omega, with angular velocity, that is our omega. And we can write the formula for center of mass, moment of inertia about the center of mass. So we can say moment of inertia about center of mass, if that is given as I, then this I will be equal to 1/12 ml square. And we assume that the elastic collision is at a distance d from the center of mass. Okay. So this distance is suppose d. Okay, here let me redraw the ball, because so let us suppose the ball is somewhere here, not the end of the rod, and its distance is d from the center of mass. So we can say that our elastic collision at a distance d from center of mass, and we are supposed to find out this d. And we are also given that after collision the stick has no rotation and only translation motion is going to take place. And so we can write it as that our after collision stick has no rotation, and for that we can say that final angular velocity is equal to 0 and only translational. So this is the basic premise of our question. And so we can divide this entire discussion into two parts. First we can discuss with respect to pre-collision, and then we come to our post-collision. So we have our pre-collision, and it is said that the center of mass is stationary. Therefore, for pre-collision with respect to a stick, we can say that our center of mass velocity is equal to 0, and angular velocity we assume as omega. Angular velocity is our omega, and the velocity of the collision point is, let us suppose, is given as v point, which will be omega times d. You can say the velocity of collision point let us call this as v point, and that will be equal to omega times d. So it means the velocity is in this direction, and that is for our v point, which is omega times d. Okay. D is the perpendicular distance between the center of mass and our the ball, and initial velocity of the ball is also equal to 0. So you can say for the ball we have its velocity is equal to 0. So it means the total linear momentum will be equal to 0. Total linear momentum is equal to 0. And then we come to our post collision. And post collision, in case of stick, we just said that our final angular velocity is equal to 0, and the center of mass velocity is supposed as v. Okay. And after collision, so this is the velocity of center of mass, that is our v, and after collision the ball velocity is supposed as u. And you can say that the ball velocity is our u. Okay. And the velocity of collision point is, because there is no rotation, so velocity of the collision point will be nothing but velocity of center of mass. Okay, so we have ball velocity as u, and you can say that our velocity of collision point after will be equal to v, and there is no rotation. Okay. So we can use the conservation of linear momentum. Conservation of linear momentum, and initial momentum was equal to 0. So we can say 0 is equal to our linear momentum of the rod plus linear momentum of our ball. Therefore, from here we can say that v is equal to minus of u. It means rod and ball will be traveling with the same velocity but in opposite direction. Let us call this equation number 1. Now our collision is given as elastic. Therefore, we can say that we are given that we are having our elastic collision, or for that we can write the coefficient of restitution will be equal to 1. And from here we can write the relative velocity of approach, relative velocity of approach, that is our v point in minus 0 will be equal to omega times t, and we can find out the relative velocity of separation, relative velocity of separation, that will be equal to our u minus v is equal to omega times d, and let us call this equation number 2. And now we just found out that our equation number 1, that v is equal to minus of u. So we can easily substitute it. So we can say from equation 1, we can write that our u is equal to minus of minus u is equal to omega d, and therefore we can say that u is equal to, and will be equal to our omega d by 2, or we can say our v is equal to minus omega d upon 2. Now this is the velocity, respective velocity of our stick as well as our ball, and we have to keep in mind that our stick is not rotating. Okay, so rotational velocity is, there is no rotational motion basically in the stick. And now we can use our angular momentum part. So we can say angular momentum about center of mass of the stick, angular momentum about center of mass of stick. And in this case we can use the concept of our impulse. So let us assume that there is an impulse J which is from the ball which acts on the stick. So we can say we are having a impulse represented as J from ball acts on sticks. Acts on stick. And this impulse J will be acting at a distance of d from the center of mass, because the ball is at a distance d from the center of mass. Okay, so this is our ball and this is a distance d. So impulse will be obviously acting at a distance d from the center of mass. Therefore, we can write the equation for our angular impulse, or we can say the torque equation, that can be also written with the help of that. And so we can say that our angular impulse, and angular impulse we can put it like, because the stick is pushing the ball toward the right side, rightwards we can say, and therefore we can say that the ball is going to push the stick leftwards in the opposite direction, action reaction. Okay. And angular impulse, so from here we can say that there will be a torque direction, and which is going to oppose the rotation. Torque direction opposes rotation. Opposes rotation. And so you can say that if the collision point is on the right side, as in the figure also, we can say that ball pushes stick leftward. So it means the impulse on the stick will be towards the leftward. Therefore, you can say that impulse on stick is leftward. Therefore, we can say that our angular momentum, so we can say that our delta L will be equal to minus of J times the distance D. And we can also find out our initial angular momentum. Initial angular momentum about center of mass, let us call this as L of I. Initial will be equal to I times omega, and I we already know is our half 1 by 12 ml square times omega. And final, we know that its angular velocity is equal to 0, so final angular momentum will be equal to 0. And you can say that our angular velocity final is equal to 0. Therefore, final angular momentum is equal to 0. So it means we are having, let me write it, final angular momentum, that is L of F is equal to 0. So their change in momentum, that is the difference between the two, we can write this as our substituting this equation, we get our 0 minus 1 upon 12 ml square omega will be equal to our minus J times D. And from here we can say that our impulse is equal to 1 upon 12 ml square divided by d and multiply by omega. And let us call this as equation number 4. And we can also find out the impulse on the ball also. And we can say that impulse on ball and we have our, initially it was at rest and then it is moving with the velocity u. So that is change is equal to our j. And from here we can say that our u is equal to j upon m. And j we just found out, therefore we can write that u is equal to, this is our 1 upon m and j is 1 upon 12 ml square d times omega. And this mass and mass cancels out, so we get this as 1 upon 12 L square upon d times omega. And we have two equations of u and we can equate both these equations. And the first equation is our this omega d by 2, and second equation we just found out, right? But u is equal to omega d upon 2, so which is equal to 1 upon 12 L square d upon omega. And here this omega cancels out, and this gives us that we will get here d square, and this goes by 6, so we get our d will be equal to L upon square root of 6. So this is the distance at which the stick is going to strike the ball such that there is no translational motion in the stick, only rotational motion is going to take place. Okay, if you require we can rationalize it, that depends upon the answer, what are options given to us. Now we come to the second question. In this question it states that you hold one end of a uniform stick of length L. The stick is struck sharply at some point along the length with a hammer. At what location should the blow be delivered so that the end you are holding remains momentarily at rest immediately after the impact, which means you feel no sting on your hand. This special point is called as a center of percussion. Okay, so it means, because normally as soon as we hit the stick we are going to feel the reaction basically on our hand. Okay, that is called as a sting, and that point is called as a center of percussion. And we are supposed to find out what will be that distance. And so we can just draw this approximate figure for that. So this is stick of length L, and let us assume that its mass is small m, not given to in the question, but we can assume it. Okay. And so let us assume that, okay, we come to the later on. So we are given that we have a stick whose mass is our m and length is capital L. And in this case the hand is like a pivot point. Okay. And So as soon as the hammer is going to deliver the impulse, and we can assume let the distance between the impulse point and the hand is suppose x. So we can say that the hammer delivers impulse J perpendicular to the stick at a distance x from held end. So for that, let us assume that we are holding the stick from somewhere here, and the hammer is impulse is provided at distance x. So at this point is our impulse, and this is the holding point. And so basically there should be no sting in the hand, or we can say the held hand, the held end has zero velocity, okay, right after the impulse. This is the basic meaning of that. So we can say that our held end has zero velocity right after the impulse, right after the impulse, and which basically means no sting. That is a term used in the question. And like we said, that distance is x, and this point is nothing but our center of percussion. Okay, we can call this as COP. And so in this case, we are going to use the concept of our linear momentum and the angular momentum, and there should be no rotation about the center of percussion. So rod should not be moving about or pivoting about the center of percussion. Okay. So let us assume that this COP is our point A. Okay. So let me draw this separately. So we have this as COP, this is point A, and we say, okay, let me draw it in the different way. Okay, let me draw it this way. This is much more easier to visualize the coordinates. And so this is our point A, and we are calling this point A x is equal to 0. And below is at point B. Suppose this is point B, and the distance between the two is nothing but our x. And the center of mass from our A, let me, this is our point A at extreme end, and so this is about point A, and the center of mass it has a distance of L/2 from A. So we can just, and let us say that our held end is our point A, and this point A is at x is equal to 0. And we have our hammer at point B, and which is at a distance x from A. And we can say that our center of mass is at L by 2 from A. So it means we can find out the moment of inertia about this point A, because we already know the moment of inertia about the center of mass, and then we can use the parallel axis theorem to find out the moment of inertia about point A. So we can say that moment of inertia about A, let us call this as IA, which will be equal to moment of inertia about the center of mass plus mass of the rod and the distance between the two whole square. Okay. And ICM is our 1 upon 12 ml square, plus this also come as, we have this as ml square upon 4. So we get that the moment of inertia about the point A will be equal to, this will be 12 and 3 plus 4, so this will become 1 by 3 ml square. So this is the moment of inertia about point A, it means the point which we are holding. Now we come to our impulse motion, or rather we can say post impulse motion. Because the pre-impulse motion, everything is at rest. Okay, so there is not much of the discussion to be carried out in the pre-impulse motion. And post-impulse, we are having a impulse at B, impulse at B, and let us suppose that is our J. And because of this, we can say that the linear velocity of the center of mass, let us call this as VCM, which will be equal to J upon M. And we can also find out we can say that the angular velocity is omega. Okay, not given the question, but we can say that the angular velocity is equal to omega. But we are interested in to make analysis of the rotation about point A. Okay, that is our main goal here. So we can say that rotation about point A, rotation about point A, and which is our held end. Therefore, we can write that because the impulse is at a distance at point B, and this B is x distance from A. Therefore, we can say that our impulse J is at distance x from A. Therefore, we can write that the angular impulse will be equal to j times x. And initial angular momentum about point A is 0 because it is stationary. Okay, entire system is stationary. You can say pre impulse. Therefore, we can say that our initial angular momentum about point A, initial angular momentum about A is equal to 0, and final angular momentum about point A, we can say that our moment of inertia about point A and the angular velocity with respect to point A. Therefore, we can write that our j of x will be equal to the change in momentum. Initial was 0, final is I omega. So, this comes as IA omega A. IA we just calculated is our 1 by 3 ml square times omega A. So, from here we can say that the angular velocity of A is equal to 3jx upon ml square. Let us call this equation number 1. Now we come to our velocity at the point A, which is our point of percussion. Okay. So we can say velocity of point A, which is our held end, and the stick is going to rotate about the instantaneous center. Okay, that's the basic thing that it tends to do. So we can say the stick rotates about instantaneous center. Instantaneous center, but we want that this point A should be having the velocity is equal to 0. So we can say, but we want that velocity at A should be equal to 0. And we can say that the velocity at A will be equal to, due to the translational motion of the center of mass as well as the rotational motion about the center of mass. Okay. So we can say that our velocity of point A is velocity due to and we can write this as our translational motion of center of mass, which we already calculated. Velocity of center of mass is equal to j upon m, and we have our secondary, that is rotation about center of mass. Rotation about center of mass, and which is at a distance L by 2 from the center of mass, and its angular velocity we have already said that it is to omega at L by 2 from the center of mass. Okay, because this A point is at the, this is our A point. Okay, so its velocity we have said that it is our omega. and therefore we can find out the velocity of A relative to the center of mass. So we can say the velocity of A relative to center of mass will be equal to, obviously in the our opposite to our the impulse, that is because of the hammer, so that will be minus omega and L by 2, okay, and that is opposite to the blow. Blow is because of the hammer. Therefore, the total velocity at A, total velocity at A will be equal to, let us call this as VA, and that will be equal to our velocity of center of mass minus omega L by 2, and we want that this VA should be equal to 0. So we can say, but VA should be equal to 0. Therefore, we can write that our VCM we just calculated G upon M, so we can substitute here also, so we get 0 is equal to J upon M minus omega L by 2. So this gives us that J upon M is equal to omega L by 2, and let us call this as equation number 2. And now we come to our angular momentum about the center of mass. Okay. Angular momentum about the center of mass, and the impulse, that is J, is at a distance of x minus L by 2 from the center of mass. So you can say that our impulse J is at a distance x minus L by 2 from center of mass, which basically means that the angular impulse about the center of mass angular impulse about the center of mass, and that is equal to J times x minus L by 2, and which is also equal to our ICM times omega, and we can just substitute the value, so we get this as our J x minus L by 2 is equal to our ICM omega. ICM we already know is our 1 by 12 m L square omega. Therefore, from here we can write that our omega is equal to, we get this as our 12 times J x minus L by 2 divided by m L square. Let us call this equation number 3. And we already have equation number 2. In this, we are going to substitute value of omega from equation 3. Therefore, we can write from equation 2 and 3, from equation 2 and 3, we can write that our J upon omega is equal to, J upon M is equal to omega is our 12J x minus L by 2 divided by m L square and this is multiplied by L by 2. And we can cancel out here, this square goes by L, and M, J and J, therefore we get that our 1 is equal to, and we can also cancel out our, goes by 6. So this comes as 6x minus L by 2 and divided by L. Now it's a simple calculations. So we get this, our L is equal to our 6x minus 3L. So this gives us, this will be coming as 4L, and x will be equal to 4 by 6 time L, which is nothing but 2 by 3 L. Okay. So it means the hammer blow should be at a distance of 2 by 3 L. Okay. We have to keep in mind that initially, because it solves lot of problem, we can assume this point A anywhere on this rod, okay, at any point. But for the ease of calculation, we assume that this is at the extreme. Okay, we can assume at any point, and this helps us because we took this initial coordinate as x is equal to 0. Okay. And so if we take another point, the calculation will be a little bit typical, but answer will be same. Okay. So this was our second question. So this completes our all the 2 questions for today. And in this case particularly, we have to remember that the particular term which is used is our center of percussion. Okay. So which basically means that striking here causes no reaction force or motion at the held end. Okay. Once we are holding, that end is having the no reaction force. Okay. That's the basic meaning of the center of percussion. So this completes 2 questions. Thank you.